So today's lecture is about stereo correspondence. Okay, so remember that we basically started this chapter talking about how can you bootstrap your way up from just a few sparse correspondences to a dense correspondence, and we talked about kind of parametric ways of doing that, such as a projective transformation. Then we said, okay, well, in the real world, correspondence is not usually modeled by a single nice parametric transformation. Usually you need to compute what's called the optical flow between two images, which means that for every pixel, I need to figure out where does that pixel go in the next frame, right? Then, the last lecture, we introduced the idea of when the cameras are in this particular configuration where they're, two cameras separated in space looking at the same scene at the same time, the correspondence is in fact constrained by this thing that we talked about called the epipolar geometry, right? So last time we talked about epipolar lines in the fundamental matrix and how that means that instead of searching all over the place for correspondence, you only have to search along the epipolar lines, right? So basically the setup is the following. So this is the topic, is stereo correspondence. And the setup is that we have a pair of images, and we're going to assume that these images are rectified, right? We talked about this at the end of last class. This is basically saying that we transform the images initially so that the epipolar lines are horizontal lines that coincide with the rows of the image, right? That's going to make our life much easier because really all we have to do is solve the problem of along each row what pixel corresponds to what. So basically we're going to assume images are rectified. And what that means is epipolar lines are equal to the rows or the scan lines of the image. And then the problem becomes a little bit more like a set of, well, you could solve it as a set of one-dimensional problems. In practice, we still want to tie those one-dimensional problems carefully together to prevent the solutions at different lines from being totally independent. But the basic idea is that for every pixel over here, I need to compute kind of, instead of a u comma v, I need to compute one distance, right? I have to decide, okay, where did that pixel go, right? So I'm only computing one dimension of information, and that dimension is called the disparity, okay? So for each pixel, compute what's called the disparity, which we define as d equals x minus x prime. So that's kind of like saying that in image 1 we have x comma y, and in image 2 we have x prime comma y, right? And the y's are the same because we've assumed that everything is rectified. That means that every row of the first image corresponds with this corresponding row in the second image. And you can kind of see here that what I'm using is kind of this kind of Cartesian coordinate system where this dimension is x and this dimension is y, right? So that's like saying that, since the y's are equal, that's like saying that they occur on the same row. This is just to be careful, though, this is kind of flipped from the way that MATLAB would index the pixels of the matrix, right? So in MATLAB, you would say, what is the row and then what is the column, right? So you have to kind of be careful to keep straight in your image processing code which way does it go, right? And depending on how you code up your stuff in C or in Python, you may have different conventions. So you have to make sure that you know which way you're going. Okay, so what makes this problem easier to solve? Because it is easier to solve. So, one thing that I will say is that, there are situations where both optical flow or stereo could be applied, right? Meaning that if I have, two cameras where the scene has not changed, either I could compute the optical flow between them or I could compute stereo correspondence if I estimated the epipolar geometry. And it's been shown that generally, in cases where you can do either one, stereo algorithms perform a lot better than optical flow algorithms. And so let me talk about a couple of the reasons why that's true. So, kind of differences between stereo and optical flow. So one is kind of like kind of a full 2D search for UV versus a 1D search for the disparity. That's kind of what we talked about already. So one is the fact that I've kind of constrained where I look for the correspondences. The second one is that typically disparities are quantized. What I mean by that is that usually we measure disparities in units of, like integer units of pixels, or if we really wanted to, we could do half pixels or quarter pixels. Right? But the point is that we're not going to be in a situation where we measure the disparity as being, 3.892 pixels, right? We're going to say it's either 3 pixels, 3.5 pixels, 3 3/4 pixels, something like that, right? That means that all the things that we're solving for are discrete solutions for disparities, right? And the fact that we can now apply things like belief propagation or graph cuts to those kinds of discrete optimization problems makes the solutions a lot easier to come by, right? Whereas in optical flow, typically the UV vectors are not quantized at all. They're just like random, or not random, but they're just continuous numbers, right? So this basically allows things like graph cuts and loopy belief propagation. We'll talk about that in a few seconds. So one thing that I swept under the rug in the optical flow part is what happens when you have occlusions, right? So one thing I talked about in the optical flow section was, well, you could probably figure out maybe that you had an occlusion because if you compute the flow vector forward and the flow vector backward, they don't match up. But that doesn't necessarily really help you model the occlusions. And so one thing that happens a lot in stereo is that occlusions are modeled explicitly. Again, we'll talk about that a little bit in a second. It totally depends on your camera setup, but there are often some simplifying assumptions that you can make to even make the stereo problem easier, right? One such simplifying assumption is, we might be able to impose monotonicity constraints. And I'll talk about exactly what that means in a moment with a picture. But basically, in words, what this means is that we may be able to make a simplifying assumption that correspondences occur along epipolar lines in the same order, right? And in cases where, all the stuff in the scene is kind of sufficiently far away from the camera, you may be able to get away with that assumption and make your correspondence problem even easier. But for stuff that's close to the camera and you have little thin wires and stuff, then you may not be able to do that. So I'll show you some pictures about that in a second. So the other thing is that, to do stereo, you must either calibrate the cameras or estimate epipolar lines. Right? What I mean by that is that when I do an optical flow algorithm, fundamentally I don't need to know anything about how those cameras that took the images were related, right? But for a stereo algorithm, I need to be able to rectify the images, meaning that I need to know where are these epipolar lines in the first place. And so we talked last time about how you could do that. If I had a bunch of point correspondences, how do we estimate the fundamental matrix? And the fundamental matrix gives us the epipolar lines. So that's not the end of the world, but you do need to have a little bit more information about the setup. And in stereo correspondence, actually, a lot of times you do have that information because, for example, you can buy a kind of all-in-one stereo rig. I have one in my lab where it's basically a rigid casing around a pair of cameras, and the calibration of those cameras is never going to go out of whack because they are forced to always be aligned by this rigid bar, right? And so in that case, you can rely on the images coming out of the camera not needing to be calibrated every time. You can kind of say, okay, I know that these cameras are calibrated. And in the same way, when the Hollywood guys, build a stereo rig with two cameras that kind of have slightly different optical paths, there's a calibration process there too. And we're going to talk more about that process next week. So basically, as I said last time, we're now going to get into some of the more camera and 3D related stuff. And so one of the first things we're going to talk about in Chapter 6 is camera calibration, right? How do you kind of know the parameters of your camera from observing the scene? Things like, 3D position, lens distortion, image parameters, and so on. So we're going to talk all about that probably starting on next Thursday. Okay. The final thing is that it's critical to note that the images for stereo must be taken simultaneously. And that's kind of a critical assumption, right? We know that the whole hypothesis about stereo is that either nothing in the scene is moving at all, in which case there's no, in which case time is not a factor, or the cameras acquired the image of the world at exactly the same time, right? If that assumption is not true, right, so if, for example, I take a picture with my camera, you guys all move around, and then I take another picture with my camera from a different position, that doesn't satisfy the requirements of stereo, right? So, if those assumptions are not satisfied, you may end up with correspondences that don't really make any sense because you haven't, obeyed the rules. Okay, so any questions about the big picture? All right, so what I want to talk about first are some kind of very basic ideas that underlay some of the first stereo algorithms, okay? So, these are not ideas that are going to get you all the way there for kind of the best performing stereo algorithms of the day, but this is kind of the basic idea. So the simplest thing that you could imagine doing would be, okay, so here's my row that I want to look at right now. I take this point, and I want to figure out what is the best point over there in image number 2, right? And so the, easiest thing I could do would be to say, okay, I'm going to build a little window around here, and I'm going to search for the best matching window over here, right? Super easy. And so I would call this, so there are a couple things we could do. We could compare all the pixels and look at the sum of squares distance. That's the kind of thing that happens a lot in some of the algorithms we talked about earlier. In stereo, you often see what's called basically the sum of absolute distances. So I'd say the sum of absolute distances is, so for a point over here, let's call this point x0, y0. So if I start at this point in image 1, and I'm looking at this candidate D, what I would do is I would say, okay, well, I'm going to look at the sum over all the pixels in some window around D, the difference between the pixel over here and some pixel over here. And the reason it's called the sum of absolute distances is here I'm just taking the absolute value of that difference instead of squaring it. And part of the reason is that you can still get good stereo performance by looking at just the absolute value of the distance, and you avoid some computations having to square stuff or take the square root of stuff, right? And so, this window is kind of up to you. You could either make it literally a square window around the pixel, so it's, even though I'm doing the correspondence row by row, this method here is at least taking into account some of what's happening above the row and below the row for some sort of consistency. If I wanted to, I could just look at exactly what's happening along the row, but that would probably lead to stereo maps that were really what I would call streaky, right? Meaning that you have these kind of almost independent calculations along each row. And you don't want this kind of streakiness. You want to have like nice looking stereo maps. I'll show you some examples of that in a second. So this would be the sum of absolute differences. Another more complicated method, which is one I think I asked you to look at in the homework, is called the Birchfield-Tomasi measure. And so kind of what that means is that instead of only allowing myself to click the window along units of pixels, what the Birchfield-Tomasi measure tries to do is basically say, okay, so suppose that my disparity was measured in units of pixels, I could still get a good estimate by letting myself kind of try and fit this window. So if I make a zoomed in version, so let's take a look at, like, say I've got a 3x3 window, and say I'm asking myself about the match to this window here. So Birchfield-Tomasi would basically say, okay, well, I can compare the window over from image 1 to this window here, and I can also kind of hypothesize what would happen if I moved over half a pixel. So kind of like interpolating between this pixel and this pixel to get a value here. Or I could move half a pixel over and look at this window shifted over a little bit. So basically, it's a way of kind of doing a little bit of sub-pixel interpolation, even though the disparities are only measured in full pixels, right? And so this helps me get a little bit more of an accurate, decision about whether two windows should match by letting the windows on both sides kind of, jiggle a little bit by half a pixel. Okay. And so you'll figure this out a little bit more when you kind of, the equation for the Birchfield-Tomasi measure is a little bit hairy to look at, but I gave you a homework problem where you kind of have some real numbers to work with, and you can kind of see how to make the match work out. Okay, so I think that will become clearer as you start working on the homework. Another thing that you can do that I think is actually a pretty good idea is called the Census transform. And for that, let me show you a picture. And so the idea here is that suppose that the top block is the set of pixels from image 1 and the bottom block is a set of pixels from image 2. And the idea here is that, again, it could be, although realistically for stereo cameras that are looking at the same scene at the same time, you don't expect illumination to have that much of a factor. But if you've got a static scene that you move the camera in between and there's some time interval between the motion of the camera, then there could be some illumination artifacts. And so what's happening here is you say, okay, well, here is my 3x3 block centered at a pixel of interest. And what I do is, instead of actually writing down the actual pixel intensity values around the center pixel, what I do instead is I just make a little path of am I brighter or darker than the center pixel? So I make a little binary code that says if I'm darker, I'm 0, and if I'm brighter, I'm 1. So for example, if I follow this around, this is like saying, okay, 50 is darker than 100, so my first bit is 0. This is darker than 100, so I have 0, 0, 1, 1, 1, 0, 0. And so I encode this block by this bit pattern of lighter or darker than, for the neighbors. And so that's what they call the census transform of that block. And then I do the same thing for a candidate guy down here. This is like saying, okay, well, here's a place where I could match this block to. Again, what have I got? I've got 0, darker, 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 lighter, lighter, darker, lighter, right? And so I have another bit string, and then instead of directly comparing, 50 to 60, what I'm doing instead is I'm saying, do my bit strings match or not for the given neighborhood pixel, right? So in this case, I'm saying, okay, well, these two bit strings differ by 2 bits out of the 8, right? In this case, for example, this guy over here was lighter, and it was darker over here, right? And so the idea is that this is a little bit more robust to the exact pixel values, but still gets the idea across of does the intensity pattern around the pixel match up, right? And so that's a kind of a clever idea, and many good stereo algorithms are based on this idea instead of things like the sum of absolute differences. So that's worth taking a look at. So one issue with any of the stuff I just told you is that the decision about whether or not, the decision about the best match for a given pixel, the way I've explained so far, is basically independent at every pixel along the scan line, right? And so, these, naively are what I would call winner-take-all approaches. And what that means is, suppose that I have, in this case, so here is my scan line, suppose I have like a box like this, in the scene, and I say, okay, well, here, this guy, the best match is this. And maybe here, since this box face is just a blank, blank featureless front, maybe, the best match to this guy is also this block, right? If I just basically process every pixel along the scan line independently, there's nothing to prevent multiple blocks from the first image from matching to the same place in the second image, right? And we know that physically that doesn't make any sense, right? We want to somehow prevent there from being, collisions of matches, right? In some sense, we want to say, okay, every pixel in image 1 can match to at most one pixel in image 2, and vice versa. You can't have anything where multiple pixels are matching to the same place. So we want to enforce something like that. So what can we do? Well, one idea, very simple idea, is to use something like dynamic programming. So we can use dynamic programming to kind of force pixels to match kind of globally along the scan line. Kind of what I'd like to be able to say is that, I want to make a decision about all the matches along the scan line at once in such a way that, taken across the whole scan line, I have the best match possible, instead of saying that for every pixel along the scan line, I'm independently choosing the best match. And so this is a sketch of how that might work. So here's the idea. So there are two images on the top and the bottom, right? The same object or the same scene looked at from different perspectives. Right here, it's like a box that's in a corner, and there's a stripe of white paint on the wall. Okay, so if I look at the scan line in image 1, I have basically this pattern of, here's the wall, here's the front face of the box, here's the side face, or here's the top of the box, side face of the box, wall, stripe, wall, and over here I've got kind of the same pattern: wall, side, top, side, wall again. You can see that in this case, from this perspective, I don't see the stripe because it's occluded by the box, right? But I can imagine what I want to do is I want to match this entire scan line to this entire scan line over here, right? And how would I do that? Well, one way that you can think about doing this is is dynamic programming, right? The idea being that I want to find so I can represent a matching by a path that goes from the lower left-hand corner of this graph to the upper right-hand corner, right? That's like saying I start matching both scan lines at the left edge, and they both have to end at the right edge, and along the way I have to generate some sort of a correspondence between the two scan lines at the same time, right? And so what I've drawn here would be like the best correspondence, right? Where I'm matching all the points along the wall, then I match all the points along the side face of the box, and then along the top and along the side. And here, there's a little bit of a horizontal line that says, well, nothing over in image 2 matches in image 1 in this region because of occlusion, right? So occlusions in one image or the other are going to cause me to have vertical or horizontal paths in this matching path. And then here, the correspondence is picked up again. Okay? And so kind of what's happening here is that what I want to do is I want to minimize from the left-hand edge to the right-hand edge the cost of each of the pixels and the guess about the disparity. Right? So this is like kind of a minimization over the set of Ds, right? And so here, for this cost function, I could plug in whatever I want. I could plug in the sum of absolute distances. I could plug in the census transform. Basically, what I have is a cost function that tells me for every pixel how good is the match. And then I want to minimize the sum of all those goodnesses all at once, right? And so dynamic programming is a way to do that. However, one of the problems is that if you look back at my picture, this makes a strong assumption that matches occur along the scan lines in the same order, right? And that is what's called the monotonicity assumption. And in this case, we don't seem to have a problem with that, right? Because if we're willing to tolerate horizontal and vertical parts of the matching path that correspond to occlusions, this is monotonic, meaning that the path goes from the lower left to the upper right, and it never kind of doubles back on itself, right? But you can have kind of scenes like this where the matching path actually does double back on itself in real life, right? So for example, here I've got this thin pole in front of a wall. From the left-hand camera, the pole is to the right of this cross point, and from the right-hand camera, the pole is to the left of the cross point. And this is sometimes called the double nail illusion. So basically, if you take your two fingers and you hold them out in front of your face like this, and you kind of alternate your eyes, if you do it the right way, so you kind of blink in one direction, and the far finger is to the left, and you blink in the other direction, the far finger is to the right, right? And so this is something that is kind of like a corner case in machine vision, right? So you have this kind of problem when you're, for example, like looking through a picket fence at a background that's far away, right? That you can get these weird correspondence switches and so on. So in those cases, kind of life is hard. There's no question about it. But in kind of non-pathological situations, hopefully it doesn't happen to you that often. In cases where I've got something like this, a normal stereo camera, so you can think about your eyes as a stereo camera, right? That's exactly what's happening. If I switch back and forth between my eyes looking at you guys, I'm not seeing this weird switching back and forth of ordering, only for stuff that's really close to my face, right? And so that's the way that a lot of stereo cameras for filming work, is that, you may have some foreground objects, but the foreground objects are not like pathologically thin wires necessarily, right? But it is something you have to think about when it comes to these kinds of algorithms. So this algorithm, and I have to say that I spent a lot of time with this algorithm in grad school, so this is basically what I just described would be what I would call the Ohta-Kanade algorithm. But, one issue with this is that still I'm solving this dynamic programming problem fundamentally, the way I described it just now, fundamentally independently at each scan line, right? That means that there's really nothing that forces the scan lines to agree, and that's a problem, right? Because whenever you have something that really is only going, scan line to scan line independently, you run the risk of getting, like I said, these streaky artifacts in the stereo map where the disparities at one scan line, don't really match up very well with the disparities in the next scan line. Kind of what I want is, even though I know that I have these constraints, I still need to solve the problem in a little bit more of a two-dimensional way than just processing a series of one-dimensional problems, okay? And so that's where some of the more modern algorithms come in for stereo. Okay, so let's talk about how we would kind of extend things a little bit. Well, one thing that we talked about a lot in the first couple chapters as a optimization algorithm that lots of people are using in computer vision now is graph cuts, right? So graph cuts we started talking about in the world of, I guess we talked about it a little bit in terms of like grab cut when we were doing segmentation and mapping, right? We were talking about, okay, I want to decide, is this pixel got a value of 1 for being in the foreground, or does it have a value of 0 for being in the background, right? And we devised this problem that says, okay, at every pixel there is something that says, what is my kind of prior opinion about whether this should be foreground or background based on the color of the pixel. And then I had another term that said, I want that foreground-background map to be smooth so that if my neighbors are all foreground, there's a heavy expectation that I should also be foreground, right? So there's kind of a data term, and there's kind of a regularization or neighborhood term that forces nearby pixels to have the same values, okay? And so to kind of write down what I just said in words, kind of scan line by scan line disparity maps are often streaky. And let me see if I can find an instance of that. So there is a at Middlebury, so I keep on coming back to these Middlebury data sets because they've done so much in the way of kind of benchmarking computer vision algorithms. So here is the Middlebury stereo evaluation database, where again, if you look and see the kinds of data sets they provide stereo pairs with known ground truth. And so, for example, here you can see that this is a stereo pair. There's a bunch of cones and some sort of a tiki statue or something. And you can see that these, while these look kind of similar, like here the cone is definitely to the left of the tiki, or definitely to the right of the tiki head, and here the cone is just on the edge of the tiki head. So these are a stereo pair of cameras with known disparity. And so here, basically, a lighter color in the disparity map means that there's more of a difference between the two x values, and darker means that the two x values are almost the same. And so, again, at Middlebury, they will provide you with a bunch of known stereo pairs that you can benchmark your algorithm on. And then, if you go back, you can see that there is this whole evaluation database of kind of the top stereo algorithms evaluated on various data sets. And so here, I'm not sure if I can, so let's go back to the bottom of the list, right? So I'm not sure whether even Ohta and Kanade is still on this list. No matches found. Okay, so let's see if we can find some bad algorithm. Here, like 1B, that was what we want. So 1B should not be very good. That's kind of basically what I just described. DP, okay. No, thank you. So I think that I can see some disparity maps here, right? So this is what I mean by streaky, right? So if I do what I just told you with the dynamic programming, you know, I get something that looks not bad, right? So you can see this is a table lamp, and there's a statue behind it, and there's a camera behind it over here, and there's some stuff on the desk. So you get the general gist of what's going on in the scene, right? But, you know, you can see that there's all these kind of horizontal line artifacts that come from the fact that I'm not really enforcing that what happens between scan lines is consistent, right? Let's look at the corresponding stereo map for like a disparity map for a top performing algorithm. So if I go up to the top and look at the same sort of ground truth, the same sort of thing, this is like a much nicer disparity map because you can see that there's none of this kind of streaky artifact. I have all the objects that have like nice, well-defined shapes. There's no, you know, weird blobs in the middle. You know, I can see the edge of this table lamp looks really good, right? So this is kind of, you know, a much better disparity map, and that's the kind of thing that we want to go for. And you can see that if you poke around the site, that you can get all sorts of, you know, here's the cones that we were looking at earlier, right? So here's the disparity map for the cone example. I guess I should have made that example a little bit bigger on the screen. But you can see that this is, you know, a good thing, right? This is a good thing. And I think that, you know, also, we're going to talk about this a little bit more next time, but you can certainly imagine that, you know, why do you want a good stereo map? So, for example, in the non-visual effects world, I could use this type of stereo map for something like robot navigation, right? I put a stereo camera in the front of my robot, it drives around and estimates, you know, the disparities, and the disparities are kind of like a surrogate for distances to things, right? So here, even though I don't necessarily know exactly how far these cones are away from the camera, I know they're close to me, right? And so you can imagine a crude robot control algorithm, maybe like your Roomba or something, that is driving around, and when it sees something that has a high disparity in front of it, it turns to avoid it, right? So you can make a little, you know, driving around algorithm based on that. Okay, so we'll talk a little more about, you know, literal 3D sensing later on in the course, but, you know, stereo in some sense forms the basis for some of those 3D algorithms, because if I know exactly where the cameras are, I can kind of triangulate through corresponding points to actually get real-world points in 3D. So I can actually jump from a disparity map like this to a literal 3D map with real distances in meters. Okay, so, well, I guess I'm on this page. So again, the same idea. So you, I guess here, actually, if you ever want to do stereo yourself, there's some stereo code that you can download. If you want to evaluate your own stereo algorithm, you basically have to write some code that conforms to an API, or I guess actually here it seems like maybe you just upload your disparity map. And here you can see actually that this gives you some sense. So here, the Scuba database, the Scuba stereo set, the one that had the head and the table lamp, you can see that here, that is constrained to have only 16 levels of disparity, right? So that you can basically say from 0 to 15 are your allowable disparity levels. So that's a very constrained problem, right? Instead of trying to estimate the, you know, decimal value of some UV map for a optical flow algorithm, you really only have to say for every pixel how many pixels away between 0 and 16 are you on the other image. These other ones have a little bit of a higher disparity range, between like 0 and 59 for the cones one. Yeah, so basically you specify your disparity maps, and then you get on the big board. And there are lots of ways of evaluating how good your stereo algorithm is. And so, for example, I'd have to, I don't want to make something up, but here, basically, this, for example, is like looking at the quality of the performance over all the places where it is possible to estimate a disparity. Because it's not possible to give you a disparity number for something that is included in one image and visible in the other image, right? So, for example, here, there are a bunch of things behind the table lamp that, you know, one of the images never saw, and so I can't evaluate the performance of a stereo algorithm on those occluded pixels. And so here, this is kind of like saying that my measure is, you know, 0.87 over all non-occluded pixels, right? And if I decide to sort by, you know, there's also, you know, some maps where some stereo algorithms will explicitly tell you this is where I think the occlusions are in the image, and there are metrics for kind of deciding how well an algorithm did on that also. Okay, so that's the Middlebury Stereo database. So let's talk a little about how, you know, some of the building blocks for making better stereo algorithms, right? So we want to avoid this streaky problem, and so better thing to do is kind of optimization with something like graph cuts. Graph cuts or belief propagation. Right, and so when can we apply these kinds of algorithms? Well, we can apply them whenever we're in the position of an image or a computer vision problem where at every pixel we have to assign some sort of a discrete label, right? And so in the grab cut problem for the hard segmentation, that label was either 0 or 1, right? Either your foreground or your background, right? And that's the standard graph cuts problem. We also talked about in the photo montage part of the course, right, the one with all the family pictures that we put together to look nice. So in that case, there's a multi-label problem, right, where you're saying, okay, for every pixel in the composite, in the final composite, did you come from image 1, 2, 3, or 4, right? So now I've got a multiple label problem. And we learned that you can't solve that multiple label problem using exactly the same graph cuts algorithm. You have to use this alpha expansion algorithm, which basically cycles through the labels and uses a series of kind of yes or no labels to solve this problem where you've got multiple possibilities in each pixel. Okay, but again, we talked about how that algorithm works very well in practice. And the same algorithm can be applied here. So again, our labels now are disparity values. So for example, for that scuba data set, the labels are disparity 0 through 15, right? So we've got 16, you know, a family of 16 possible label sets, right? So we can apply the same algorithm here. And we also talked about how any algorithm that I can apply graph cuts to, I could also apply this belief propagation algorithm to. We'll talk about that in just a second. So how would the graph cuts algorithm work? So kind of a graph cuts approach. Well, we want a labeling, which I would call L, for all pixels in the image. And so the label at pixel I could be, you know, say 1 of 16 disparity levels. Okay. And now what I want to do is I want to say that I'm going to connect up all of the pixels in the image into a graph. Right? So I'm trying to estimate the, you know, disparity every pixel, but I also look at what are the neighbors of my pixel, right? So kind of what I have is I have nodes or vertices which I'm going to call V, and then I have edges, which I'm going to call E. And the idea is that, in this case, the edges basically could just be my north, south, east, and west neighbors of every pixel. And then what I want to do is I want to minimize a cost function across the labelings of all the pixels at once, right? So what I have is that I have like this energy function of my labeling that looks like one term that over all of the pixels in the image, I have some sort of a data term that basically says, how good is that label? And then I have another term that says, over all of the edges in the image, how, let's call it smoothness, how similar are those labels between label I and label J? Okay. And so, again, this looks very much like the kind of thing that we were talking about last time, where we have the data term. So what do these terms look like? So the data term basically comes from the stuff I talked about under the heading of basic stereo algorithms, right? So I would say that my one example of a data term for the label at pixel I could be something like, well, so let me write this a slightly different way. So I could say the data term saying that the label of pixel I is equal to D could be, for example, the sum of absolute differences cost function at the xy position corresponding to pixel I with this hypothesis D, right? Or I could make this the Birchfield-Tomasi function, or I could make this the Census transform function, right? All this is saying is that this is a function that depends on the colors or the intensities in image 1 and image 2, right? How good is the match locally between this block of pixels in image 1 and this set of pixels in image 2, right? So this is the only thing that depends on the image, right? And the smoothness term, the smoothness term could be a variety of things, right? So one thing that I could say is, well, I could say it's equal to 0 if the labels agree, and it's equal to some other big number if the labels don't agree, right? This is called the Potts model. So one thing that you're kind of doing here, the way to think about this is that I'm basically adding a constant value to the entire cost function every time my neighbors don't have don't agree across the edge, right? So the more disagreements there are, the higher the cost function is. Or I could say something that's more like this, where I say, okay, it's 0 if you guys agree. It's some cost if you don't agree, but the image, or maybe I should say and the difference between these things is big, and it's some even bigger penalty if you don't agree and the difference between these things is small. So kind of the idea here is you're saying, okay, well, if your labels between neighbors agree, no problem, no penalty. If you don't agree, then I look and say, okay, well, if your colors are really different, then I'm not going to penalize you too much, because if the colors are really different, maybe there's good evidence that there's no reason that your labeling should be the same in the first place. So you only get a penalty of K. But then I look and say, okay, well, actually, if your colors are the same, then I think there's pretty good evidence, there's a pretty good hypothesis that you guys should have the same label, and now I'm going to give you a higher penalty, right? So this is called the intensity adaptive Potts model. And of course, you could do other things, like you could just look at, you know, if I wanted to, I could look at, the absolute difference between the disparity labels. So one thing here is that, you know, all these guys, you know, it's either, you know, no penalty for being exactly the same or penalty for being different no matter how different you are. Something like this, like an absolute value, would be something along the lines of saying, okay, well, I'm going to now penalize how different your labels are, right? Which you know, stands to reason. It's like saying, okay, well, if a label difference of disparity level 2 versus disparity level 3 is not as bad as disparity level 2 versus disparity level 12, right? And so you could look at the absolute value, or you could say, okay, I'm going to look at the minimum of this absolute value and some maximum penalty. We talked a little bit last time, or maybe it was the time before, about the issues of outlier rejection. We don't want the mismatched pixels to have like a disproportionate effect on the cost function. So at some point we want to kind of cap how bad the penalty is for not matching. It turns out that if you don't cap it, your stereo algorithms don't do very well. So usually in all these stereo algorithms, the smoothest term has some sort of maxing out for, you know, it can't get any worse than this, right? You don't want something that can kind of grow without bound. Okay. So, you know, what's happening here is that what we're trying to do is, you know, if you go back to this, at a given pixel, we're basically balancing out, you know, how well does my pixel match the model given by a disparity, and then how much credence do I give to the hypothesis that the disparities of neighboring pixels have to be the same, right? So it's definitely not, you know, I mean, as you saw from the results, it's not like you are forcing every pixel to have exactly the same disparity. If you cranked up the weight on the smoothest term, that's exactly what you'd get. But here you're trying to balance the data term with the smoothest term, right? In such a way that, you know, all things being equal, you want disparities to be the same, but you're definitely willing to let evidence from the images, you know, let you make a difference in the disparity choice between neighboring pixels. And so, you know, this is actually a pretty reasonable algorithm. So let me pause and ask, any questions about this big picture? So, you know, I mean, this is not the best stereo algorithm you could make, but it's a decent stereo algorithm. Certainly better than dynamic programming, okay? Now, one thing that I'll say is that, again, to solve this problem, since basically it's a kind of a multi-label problem, we need to use alpha expansion to solve it with graph cuts. And you can refer back to one of the earlier lectures about how alpha expansion works, basically just saying that, you know, at every stage I am kind of updating, you know, should I keep the label that I have, or should I switch to this potential new disparity, right? And so if I have 16 disparities, basically what I'm doing is I'm kind of having a while loop over a for loop of 16 disparities, saying, okay, you know, for every pixel, should I stick or should I change, right? And I keep on looping through this process until all the labels have settled down, right? Again, in the two-label case, we have kind of explicit guarantees that the labeling will converge to the global minimum. In the multi-label case, we don't have the same guarantees, but in practice it works really well. And so, I mean, it wouldn't stop you from using the algorithm to not have the explicit guarantees. So, a couple twists on the basic idea. You know, one is that, well, without going into a lot of detail, you know, there's still nothing in this whole graph cut idea that would prevent me from having multiple places in image 1 that match to the same place in image 2, right? I mean, there's nothing concrete or explicit in the algorithm that prevents that from happening. If you were really concerned about that, you could build a different kind of graph cut problem where the vertices and the edges mean something different to explicitly enforce this uniqueness issue.
And you can read a little bit in the book about how you would set up that graph cut problem, but that's kind of a little bit too advanced for what I want to talk about today. Another thing to kind of remember, actually, that's a little bit tricky is that, so let me just say, you can set up a different graph cut problem to enforce uniqueness. But let me just say that uniqueness can be tricky, especially in kind of stereo when you have kind of discrete disparity labels. So for example, let's suppose that I have, again, like a couple images of a box. And so from this perspective, I'm kind of looking at the box side on. And from this perspective, actually I drew this kind of even worse than I wanted to. So here I'm going to color the front face of the box like this. From this perspective, I'm looking at the box like this. What a crappy drawing this was. Let me draw this box again. This is why I'm not an artist. So let's say something like this. Here's the front face of the box. Okay, right, so basically here, if these are my faces, in theory, all of this stuff over here has to match to the skinny piece over there, right? And so if I really explicitly say, hey, only one pixel from image 1 can match over to corresponding pixel image 2, then I've got a whole lot of image 1 pixels left over, right? And that would be kind of weird, right? So setting up those kinds of problems is a little bit tricky, right? You don't necessarily want to enforce the uniqueness directly, and it's really a little more subtle issue to figure out how to make that work. Okay, so let me just say that I think I said this verbally a couple times already, but we can also apply what I would call loopy belief propagation to stereo. And let's look back at what that means. So basically, this was the sketch I showed about belief propagation earlier. This is kind of like saying, okay, at every pixel, I have an estimate about what my disparity should be. Think about that like kind of a probability mass function of disparity values. So this is my current belief about what my disparity could be. I have high probability that's on the large end and low probability that's on the small end. And then what I do is I solicit information from my neighbors about, hey, you guys, what do you think my probability of these disparities should be? And then those guys send me some information. I fuse all that information into a new estimate for what I should be, and then I broadcast out to my neighbors, hey, now this is what I think you should be, right? So it's kind of this message passing algorithm where everyone has a histogram about themselves and about their neighbors, and eventually, by passing these messages around, these histograms converge to, they settle down, and then at the end I would say, okay, well now, after I've settled down, I'm just going to pick the disparity bin that has the highest probability, and then that gives me a stereo map, right? And so basically any algorithm that you can apply kind of alpha expansion type graph cuts to, you can also apply belief propagation to. And in theory, I think that belief propagation is, well, I guess I would say that in practice, belief propagation is very frequently used for stereo algorithms, although I think there were some studies that said that if you could apply the same algorithm for either graph cuts or belief propagation to the same problem, that generally graph cuts did a little bit better performance-wise. I mean, they're different algorithms, but I think a lot of people use belief propagation just because this is kind of a nice kind of probabilistic interpretation of what's going on, right? I kind of keep this hypothesis about what my disparities could be, and I don't make any hard decisions until the very end. That kind of has some appeal from a kind of machine learning point of view. And also I could parallelize this algorithm because I only have to have me and my neighbors. I can kind of not pay attention to what those guys are doing off in the other part of the image. And so the message passing algorithm that would need to happen to map onto stereo is kind of outlined in the book in terms of what these messages actually are, and then how you combine them. Okay. So I'm not going to say anything more about that other than the fact that we can do this, and I would hazard a guess that many, if not most, high-performing stereo algorithms use either one of these approaches. BP or graph cuts. So I did mention in the very beginning of class that there are some, in stereo, you could kind of explicitly model occlusions, right? So when I've got an occluded pixel, right, one that appears in image 1 but does not appear in image 2, there's no way for me to estimate the disparity of that pixel, right? I don't have any information. And so in that case, nothing I've said so far, for example, the standard graph cuts algorithm forces me to assign a disparity to every pixel, right? So I could, let me just say something about occlusions and discontinuities. So what I could do is I can add an occlusion map to kind of complement the disparity map. What I mean by that is that now I have a labeling that looks like this. So basically my energy of a given labeling is saying, okay, well, I'm going to look at, for all the pixels in the image that are not occluded, right? So I'm going to build a little binary occlusion map that says every pixel is either occluded, the map is 1, or it's not occluded, the map is 0. So this is like saying, okay, if I'm not occluded, I have my usual data term, and then I have my kind of smoothest term, dot, dot, dot. And then I have basically the sum over the pixels that are occluded, some sort of a cost of occlusion, right? So this is kind of like saying, okay, now my occlusion map at pixel I is either 0 or 1. And so I don't compute disparities for places where I am occluded. Instead, I add a penalty to my overall cost function that says, okay, I'll let you I'll let you be occluded, but you're going to pay a price on the overall cost function for that, right? And so this is kind of to prevent you from saying, okay, well, if all the pixels were occluded, then I wouldn't have to worry about estimating any data terms at all, right? My cost function would be really low. So you have to crank this term up to make sure that it really hurts to occlude a pixel, and you only do it if you actually can't estimate the disparity for it, right? So this is a pretty easy little innovation to make this work. And again, this is pretty easy to incorporate into belief propagation. And you could also incorporate what I would call an explicit discontinuity map. What I would say that means is basically say, okay, so if I've got my foreground person, what I do is I basically have, if you imagine these black pixels are 1s and all the rest of the pixels are 0s, you basically say, okay, I'm going to make a map that says, this guy looks like he's just got some hair now. So you can basically make a map that says, okay, 1 if this lies on a depth discontinuity, 0 if it's part of a continuous surface, and then you treat pixels that are on or near discontinuities differently than those that are on smooth surfaces, right? So for example, you would not penalize labeling differences across the discontinuities because you expect there to be some sort of a disparity corresponding to a difference in depth across discontinuities, right? So this is kind of a way to make your algorithm a little bit more robust. Instead of treating every pair of pixels across an edge the same, you treat them differently depending on whether you estimate that they're discontinuous or not, right? And one final thing that you can do to make a good stereo algorithm is to incorporate some sort of segmentation. And so what I mean by that is you can have a model within a foreground object for how smooth the disparities should be, right? So let's suppose I'm looking at a slanted wall, right? So if I'm looking at a wall, I know that for all the pixels on the wall, the disparity is just a function of that planar surface, right? The disparity is entirely predictable from a model of that 3D shape, right? And so what I could do is I could define, for example, an additional term that I would put into the cost function that would look something like this. It would look at the difference between, well, maybe a better way to say it is I would look at the difference between the, sorry, I'm just going to rewrite this. I would have a cost function that would look something like this. I've got my label, and then I could say, okay, well, I'm going to build like a nice linear model for how the disparity should change in that region. So it's like saying, okay, if I've got a person and I've got some wall behind them, if I can segment out and say, hey, all this stuff above this line belongs to the same segment, then I am going to force the disparities to obey an assumption like this, like an image planar assumption that says that everything along this segment has to have this smoothly changing disparity with a model for how that disparity changes. So it's kind of like a planar model for disparity as a function of pixel location. Right? So if I've got a flat surface, I know the disparities should change like this model. You know, if I had a curved surface, maybe I would allow myself to have some quadratic or some, terms like that. But basically, the idea is that, if I were able to somehow segment the image into foreground pieces and background, then I can put this very high prior that says, okay, no matter what your colors are, I expect you to generally change in a kind of a consistent geometric way. I expect those disparities to have a certain sort of shape, right? And so, there are a lot of good stereo algorithms that explicitly try to segment the image and then use this segmentation to enforce that within each segment the disparities are consistent. That's kind of the basic idea. So, it's worth looking into algorithms like that if you're really looking for a high-performing stereo algorithm. And this is kind of related to the discontinuity map I talked about earlier. You can say, okay, if I can outline the objects, then I try and enforce the disparity within every object to be fairly consistent. That's the idea. And so, I'm not sure what the top-performing algorithms are these days. 143, 82. It's hard to know. You have to really dig into the papers to find out which ones of these algorithms are working. But here's an example of, this submission to a conference that's happening right now is saying something about second-order smoothness priors, right? What that probably means is that there is some sort of expectation that within a given segment or a given region that there is some smoothness to the disparity map. That prevents you from getting these crazy, wacky disparities in the interior of objects. So again, you can see that given that there are 150, algorithms submitted to this database and probably 500 more algorithms that have not been submitted to the database, that stereo has been an active research problem in computer vision almost since the day that you could acquire images off of a camera, right? So there's lots and lots of research here. And giving you an hour-long presentation about it is only scratching the surface of the stereo tricks of the trade that you would need to do. So on the other hand, luckily, stereo is almost such a common thing to do that for your purposes, there's never any reason that you should have to write your own stereo algorithm. I think there are lots of ones that you can download out there. And so, it's worth thinking. I don't think that any of your projects were explicitly talking about stereo, but, if you're in a situation where you have to do image-to-image matching and nothing has changed, then you might consider trying to find an off-the-shelf stereo algorithm that will give you some useful results. Okay. So any questions about stereo? Actually, while we have a couple minutes, let me just say, so it's a little bit, one reason that you hear about stereo in visual effects has to do with 3D films, right? And so now we know about disparity, and that's a key idea for 3D filming. Now, I don't think that, to be honest, there are a lot of cases where visual effects artists are taking stereo images and necessarily estimating the disparity and then doing stuff with them later, right? Part of it is that it's very difficult to convincingly manipulate objects in 3D after the fact and make them look convincing to the audience, right? You can imagine, what I'd like to do is I'd like to take that guy in the background and bring him forward a little bit, and then I have to in-paint the background from both eyes and decide what the new stereo should be. It's a very complicated problem, right? But one thing I do have to do is that for every computer-generated element that I add into the scene, I have to make a decision about what the disparity of those elements should be so they feel like they live in the world. And it's an interesting, discussion, and I have a nice discussion in the back of my book, or in the back of this chapter, from the guy who basically was the stereo supervisor on the most recent Transformers movie, right? So that movie had some combination of stuff that was filmed in 3D and some stuff that was post-converted. But so basically the idea is that you've probably maybe seen some behind-the-scenes images in, on YouTube or watching TV. So a stereo rig for a movie camera is much more complicated than two cameras on a stick that you'd find in a computer vision laboratory, right? So what they typically do is they have like some very, heavy and expensive camera. It's not the kind of thing that you can put two of those things very close together, right? So what they usually do is, I'm sorry you can't see this for those of you that are watching the video, but you usually have some sort of a beam splitter where, you've got one camera that is looking through this kind of mirror like this, and then you've got another camera that is like 90 degrees offset that is looking through this kind of half-silvered mirror like this, and you get two optical rays that kind of mimic eyes looking out like this, except this guy is actually 90 degrees off looking through something, because you can't physically put the two cameras close enough together, they would hit each other, right? And there's all this, cords and crap coming off the cameras, right? So if you look at a stereo rig for you can see on the making of the most recent Hobbit films, there are lots of pictures of stereo rigs, and you can see what those actually look like. So one thing that's really important is what's called the interocular distance, which is basically the distance, the physical separation between the cameras, right? And so, this is a kind of complicated issue to explain. It's actually probably easier to read about it than it is to for me to explain it to you in words. But basically, just like on a movie set, so have you guys ever heard of a focus puller? So a focus puller is basically the guy who focuses the camera in the shot. So you've all seen kind of cool shots where there's character in the foreground, character in the background, and the focus shifts in the same shot from this guy to this guy, right? So usually, actually, there's one person who is maneuvering the camera, and there's one person, a separate person, who is changing the focus of the shot, not the same guy who's moving the camera, right? And so those focus pullers are, it's a very tough job to do because you're not the person who has full control over things, and so apparently focus pullers are well paid in Hollywood for doing their job well. And so now there's somebody who's also called basically the kind of, convergence puller, the person who decides what the interocular of the two cameras should be to provide the effect that you want in your stereo film. And so once you start to think about it, you kind of start to go a little bit, crazy. So basically, if you think about you here, this is you with your eyes, right? And here's the movie screen. So the concept of stereo is that you want to make stuff appear like it is either deeper into the movie screen or coming out of the movie screen at you, right? And there are some physical limitations for how big the disparity can be to make the convincing effect of something that's really in your face, right? Because at some point, like you can't have a transformer that is standing in the theater with you because the transformer is huge and you're not that far from the screen in the first place, and so it would be impossible to get disparities that were that large to make it seem like it was living right there with you.
So kind of what's constantly happening, whether you know it or not, is that the
distance between the two images that are being sent to your eyes through the 3D glasses is kind of constantly changing in the same way that you would be kind of constantly focusing your eyes at different depths to make it not uncomfortable for you to watch the movie.
And so usually you've got some disparity budget of, basically
here, when stuff is like infinitely far away, there's no disparity, right? So kind of this is about, when you're focused on something like a star in the sky, right? That's the furthest away that something could possibly be, right? Then you think about, how many levels do you have before you get up to the plane of the movie screen? And then how many levels do you have when you get in front of the movie screen, right?
So apparently, I think that I was told that for a
2K movie, like a 2,000 dimension, an image that's 2,000 pixels wide. So basically, that's like saying that you've got, some distance behind the screen and some distance in front of the screen. So basically, maybe you can say, okay, I've got 60 pixels worth of distance, maybe I can quantize the disparity every quarter of a pixel or something like that. So you really don't have like a ton of disparity levels to play with in the movie in the first place. And so for every CGI element, you have to decide, how do you put that into the scene.
And I guess actually I have to look at this for a second. So ridiculous negative disparity. So maybe I should be careful. Maybe this is what they think of as positive, this is what they think of as negative, right?
So, there are some cases where, the stuff that's pushed into the screen is much more convincing and compelling than stuff that comes out of the screen. Like usually stuff that comes out of the screen is either very subtle, like, there are some cases where, like in Gravity, Sandra Bullock reaches out for something that's kind of floating from your perspective just in front of the screen and grabs it, right? It's not like she's reaching right next to your ear. And so the stuff that has, like the gee whiz special effects, like the, people are shooting bullets and the bullets are whizzing past you, you can kind of get away with having big disparities there because it's moving so fast that you couldn't really focus on it with your eyes even if you wanted to, right? So there are some kind of trick effects where you can have stuff that kind of whizzes past you don't really notice it. But for stuff where stuff is kind of, for a sustained amount of time, feeling like in front of the screen, that's a little bit tricky to pull off because then you have to start to think about, okay, well, it's like then your mind starts to think about this window of looking through the screen as if it's actually a physical object that, something's reaching through the screen at you. That kind of suspension of disbelief is kind of tough to sustain in 3D because of what your eyes are telling you. When you're watching just a flat movie screen, you're not really thinking of like, oh, I'm looking through a window at the world and Sandra Bullock is on the other side of the window, right? But when you have a 3D movie, suddenly there's this kind of cue that your mind is going to have a hard time interpreting. And so I suggest reading a little bit about the way that the disparity kind of works in 3D movies at the end of this chapter. It was an interesting discussion. I never really thought about, for some reason I kind of assumed initially that, well, basically they just set the distance between the stereo cameras in a film to basically mimic the physical distance between my eyes, and then they just film all the stereo movies like that. But that's actually totally not the case. Over the course of a 3D movie, the apparent distance between your eyes is just changing all the time, apparently. And so it's really interesting to think about how and why that works. And to be honest, I still don't physically have my head around it totally, but it's something to think about. Okay, so that's it. Let me close down my window here. I thought I had found a way to do this, but apparently